Over 100 years ago, on November 25, 1915, Albert Einstein lectured at the Prussian Academy for the fourth time in 4 weeks. This time he can stand proudly in front of the assembled crowd and announce to them he had finally completed the equations of the General Theory of Relativity, a journey 10 years in the making. So what led Einstein to this epoch-making discovery? In 1907, 2 years after Einstein completely redefined our understanding of space and time, he sat in the patent office in Bern, Switzerland, where he had the happiest thought of his life. It was an idea that would ultimately lead him to the discovery of the General Theory of Relativity. His thought? A man falling from the roof of a building. He realized that putting air resistance aside, the freely falling individual would not feel his weight. They would feel weightless. So let's imagine our protagonist, hanging from a building, holding on to an object. As the individual goes into free fall, from his perspective, the object falls right with him, and therefore, the object appears to be hovering, as it would if he had let go of the object in outer space. The individual feels weightless, and the environment, if he looks in the local region around him, appears to behave as if there is no gravity at all. Einstein recognized that by going into the right kind of motion, free fall, you can cancel out the effect of gravity, thereby reducing our understanding of gravity to the understanding of that kind of motion. In particular, Einstein recognized that this accelerated reference frame, no longer inertial, manifests the same properties as gravity. Through extensive calculation, Einstein found that an accelerated reference frame, in the presence of gravity, can be described as curvilinear, a geometry that is curved. If this effect of gravity, the curving of space-time, can be cancelled out by a particular motion, however, this would mean that these effects are mere artifacts of the accelerated reference frame. By 1915, this thought had led him to the intrinsic connection between gravity and curvature, ultimately leading to the new theory of general relativity. This idea sets the stage for there potentially being more than 3 dimensions of space. Einstein's theory is often described in a simple and somewhat naive metaphor. Imagine a rubber sheet that is very taut. In your mind's eye, you can imagine a spherical object that rolls across the surface of the sheet in a straight line trajectory. If we place a heavy object on the rubber sheet, it becomes curved and deformed. Now when the object moves across, it will no longer follow a straight line trajectory, but rather on a curved path in the warped environment. Einstein, through the equivalence principle, generalized this notion of space and time to 4 dimensions and instead applied it to the universe. In particular, Einstein formalized space-time as a 4-dimensional structure in which the 3 dimensions of space and the single dimension of time are bound together in a single fabric of space-time. If we use this as a representation of 3-dimensional space, then we can go to a 2-dimensional analog, which is easier to visualize. The empty vacuum of space is flat when nothing is present, but when the sun appears, the fabric of space curves. The Earth is kept in orbit because it is rolling along a valley in the curved environment that the sun creates. In 1907, Einstein was already basking in the glow of already having discovered the theory of special relativity, which had various insights into the nature of space and time. Around this time, many physicists believed that gravity was already understood from the work of Isaac Newton. However, Einstein was the kind of scientist for whom there was no such thing as received wisdom that he wasn't willing to challenge, willing to think through. At this time, Einstein asked a very fundamental question: how does gravity really work? How is it that one object in the universe, like the sun, can somehow exert a pull on another object like the Earth, even though nothing is connecting them? There's effectively empty space between them. To answer this question, Einstein naturally went to Newton's Principia and opened it to the universal law of gravitation that Newton had laid down in the late 16th century. He then goes further to subheading M, to the mechanism by which gravity operates. There Newton says, to the answer of that important question, the mechanism by which gravity operates, I leave it to the consideration of the reader. Newton wrote down a formula that told us the strength of gravity, but he never told us how gravity actually exerts its pull. Most readers at this point would simply continue reading, but this is where Einstein was different. He spent 10 long years developing his General Theory of Relativity. On November 4th, 1915, Einstein gave his first lecture at the Prussian Academy, in which he forthrightly presented a flaw in his earlier work. He then describes that he is going back to earlier geometric ideas that he developed in Zurich. Einstein then pursues these mathematical ideas with incredible perseverance. In the midst of his endeavors, Einstein gets a shock that David Hilbert, a German mathematician, has found the flaws in Einstein's work. This news is quite unnerving, because for the first time, he realizes that he has serious competition in his final race towards the General Theory of Relativity. 1 week later, on November 11th, 1915, he gives a lecture for the second time to the Academy, in which he explains his progress, but at the same time he's deeply concerned that David Hilbert is now racing him to the finishing line. Hilbert wrote to Einstein to tell him that he had already found equations of the General Theory of Relativity. Einstein, distressed, redoubles his effort and shifts his focus to a long-standing problem in Newtonian gravity, which has to do with the motion of the planet Mercury. The puzzle is that Mercury's orbit does not quite close on itself the way Newtonian gravity says that it should. Instead, the trajectory of the orbit shifts by an amount of 43 arc-seconds each century. Einstein applies the equations that he has been developing for general relativity, and astonishingly, his mathematics predicts that Mercury's orbit should shift by this amount. Ecstatic, on November 18, 1915, Einstein is ready to describe his results to the Prussian Academy and explain how his theory predicts the shift. That morning, Einstein received a letter from David Hilbert that presented his work in general relativity. Einstein immediately wrote to Hilbert to rebuke his ideas, to tell him that the contents of the paper didn't contain anything unusual. Finally, on November 25, 1915, during his fourth and final lecture at the Academy, Einstein announced that he had completed the field equations. The left-hand side describes the geometry of space-time. G mu is known as the metric tensor, which fully encapsulates the structure of space and time. This in turn describes the metric, which is the notion of distance in the space being described. R is the scalar curvature, and R mu is the Ricci tensor, which encaptures the curvature of space and time. The right-hand side represents the matter moving through the space. T mu is known as the energy stress tensor, which characterizes the energy within the environment, and the equality between the two embodies the heart of Einstein's theory, that matter and energy warp the fabric of space and time. When you supplement that with the equation of a geodesic, which roughly speaking is the shortest possible trajectory through space and time, these two equations together allow you to determine how an object will move through the curved environment of space-time. In essence, Einstein describes how an object will move subject to the force of gravity. He tells us that planets warp the fabric of space-time. Einstein then says that any other object that is moving through this environment will be nudged around by the warps and curves in space-time. In particular, this is how gravity is communicated from one object to another. Warps and curves that influence the motion of another body. Now this was a triumph. This is what Einstein was working towards for almost a decade. What about Einstein's competitor, David Hilbert? He formulated his own version of Einstein's field equations, usually expressed in this form. But in his published paper in which Hilbert presented this equation, he made it abundantly clear that he believed Albert Einstein deserved credit for the discovery of general relativity, a rather magnanimous conclusion to this competitive spirit that pushed these two monumental figures to the final form of the general theory of relativity. But regardless of which equation you use, the final theory is one of the most beautiful and elegant of the 20th century. Einstein and Hilbert tell us that gravity is communicated by the shape of the universe, that this is the heart of the general theory of relativity. Shortly after Einstein published his General Theory of Relativity, on December 22, 1915, Carl Schwarzschild presented his solution to the Einstein field equations, known as the Schwarzschild metric. Schwarzschild realized that there are situations in which enough matter can be compactified to a sufficiently dense state that the resulting object would have a strong enough gravitational pull that nothing at all could escape from it, not even light. These physical objects, known as black holes, correspond to environments in space-time with infinite curvature and mass. Any observer who crosses the event horizon, known as the Schwarzschild radius, can no longer return.